did. It was a fun game on Friday night. I was happy for the girls. It was good to see, and my little JV club that I have only got 7 kids out, but they're playing really hard right now, and they won their game too. It was kind of a nice one to sit back and relax. It was kind of like playing the Vikings. We won by 26, so it was good. So. All right, my friends, let's get started here, guys. 4.6 is going to be some applications of the chain rule. Now, there's going to be a couple new rules that come up today, but guys, there's going to be some things in this where we've got to make sure we start paying attention to shortcuts. Guys, by the end of the chapter, we're going to have a shortcut cheat sheet for all derivatives we've looked at in this chapter. Okay, we've got about 2 more sections to go, but we're going to add a few more today. And this section, I really like it because it's pretty practical, but it gets into some. I think some of the derivatives we looked at lately have been pretty upper level. Would you agree with that? It's just a matter of taking the shortcut and following the rule, isn't it? Okay, so here we go with this. So make sure you're getting notes down properly and everything. So again, 4.6 is titled Applications of the Chain Rule. Question is, how do you find the derivatives of fractional powers? Have we talked about finding derivatives using power rule?
Yeah.
Have we talked about derivatives of logarithms?
No.
How about derivatives of exponentials?
Mm-hmm.
Yes? And we've talked about derivatives of trig functions, but not what?
Inverse.
Not inverse trig functions, and how they're used in real life, okay? So our job today, guys, to answer the question, we've got to be able to find the derivatives of logarithmic functions. There's a couple of ways to go about this. Remember, there's 2 types of logs. A log base 10 that we talk about. There can be any log with any base, but sometimes we talk about log base 10 a lot. What's the other type of logarithm we tend to talk about? What's this kind of log? Natural log where the base is what natural number? E. Okay, and we'll talk about that. We're going to look also derivatives of exponentials. You kind of know this one right here. So I think this top one's going to be new for you. This bottom one right here. This middle one, I think you kind of know this one. I think you kind of know that one. The next one we're going to find derivatives of inverse trig functions. This will be very new for you today. Okay, and then we're going to talk about derivative notations and use them to find real-life solutions. Guys, some of this is known as what's called related rates. Like, to give you an example, I might say my car gets 33 miles per gallon. Gas costs $2.89 per gallon. The question might be how much is it going to cost me to drive per mile? So we got to compare our miles per gallon to our dollars per gallon to figure out how much it's going to cost per mile, stuff like that. We'll talk about things like that today. Okay, so this will be pretty new for you today as well. Okay, all right, guys, let's get started here. Derivative of logarithms. There's actually 2 types of derivatives of logarithms, so we're going to put some shortcuts up here, guys. But the one that you're probably going to see most commonly is going to involve base e. It says the derivative of the natural log of x is equal to what, kids? 1 over x. Now, I'm going to give you the other one, okay? I'm going to kind of put a little line in here. If I had, say, move this over just one. If I had the derivative, d, with respect to x, of the log base b of x like this, then this derivative becomes the following. This becomes 1 over the natural log of b, base b I should say, natural log of b times x. This will be a natural log of b times x. Now guys, this rule will be the same exact thing, but this will be the natural log. What base are we talking about here? When you use natural logs, what base are we using? E. What is the natural log of e? 1. So it's like 1 times x in the bottom by this rule right here. So it's 1 over the natural log of b times what? Okay, now, it would be great if the only thing I ever had here was just an x, right? But am I going to have other types of functions other than just x? And a lot of times we call those functions, what do we substitute in for those longer functions of x? We let something equal that function. What letter do we usually choose? U. Because we go to union, right?
Yeah.
Okay, here's the real rule right here. This is going to be the important column for you guys right here. Okay, if you ever have the natural log of u, some function u in here, like maybe 6x squared plus 8x plus 7, okay, the derivative becomes u prime over u. And we'll look at some examples like that, but that's the biggie right there. Okay, it becomes u prime over u. Likewise, if you ever have the log of some base b, I don't know what the base is down here, 7, 10. If they write just log, L-O-G, with no base down there, assume what base? 10, yep, okay. If I have a log base b of some function u, like maybe 6x squared plus 8x plus 20, its derivative becomes the following. It becomes u prime over the natural log of b times the function u. Okay, they're really the same thing. The reason I don't see natural log in the top one is because the natural log of base e is just going to be what value? 1. And 1 times u in the denominator would just be u. Okay? All right, so my main concern, kids, do you have these two rules down right here for logs? Are you good on those? Let me know when you have that down. We'll run to the next one. Next one is derivatives of exponentials. We've done this before. So you guys should be well rehearsed in this one, I think. Guys, if I have a to the x, where a is some constant, the derivative of a to the x was what, Giz? So what if my function looks like the following? What if I have something of the form, say, natural log of, I didn't want to do that. I want to open an exponential. What if I had something like a to the u power? Okay, well, the derivative of a to the u becomes the following. It's u prime times the natural log of a times your function u. And we'll look at some examples that involve that right there. But again, that's going to be your general shortcut right there. All right? And eventually, like I said, guys, we'll start, well, we get towards the end of the chapter. I think especially when we get to a test over this chapter, I think it would be really good if we put a cheat sheet together on what all derivatives are that we looked at, so we're not flipping through 8 sections of notes. Just that one sheet would be good for all derivatives. Guys good with that? So we'll formulate that someday. Okay? All right, guys, so the next one, we're going to start looking at the inverse of a sine function. Okay, now guys, most times we would write the inverse of sine function as sine. You guys remember what exponent we used for inverses before? Like that -1 exponent, right? We would read that as sine inverse of some function, in this case x. What I want you to understand is this. Sine inverse of x, just like this, is the exact same as this term up here that we call arc sine of x. So if you ever see that word arc in front of the trig function, that just means we're talking about the inverse function of it. Okay? So it says the derivative of the inverse of the sine function is what, kids?
1 minus x squared, or 1, yeah.
Over the square root of 1 minus x squared, right? Now this would be fine and dandy if the only thing I ever had out here was what variable for a function? X. But are we always going to have just an x right there? Or could we have some other function in the form of x? Well, what we say right here then is this. If we have a function that's the arc sine of u, where u is some more complex function, or maybe a composite function, then its derivative becomes the following. And it's really pretty simple. Guys, what if I asked you the question, what's the derivative of x right here? 1. Didn't they kind of do a u prime right there to get that 1 up top there? It's going to be u prime over the square root of 1 minus your function u to what power? Okay, so that's going to be the derivative of your inverse sine. Nice thing about the derivative of trig functions, we're only going to focus on 2. We're not going to focus on all 6 of them like we have in the past. That's good news, isn't it? Someone over there is excited about that. Okay. Anybody want to guess what, based on what the derivative of the inverse tangent of just x is? Anybody want to guess what the derivative of the inverse tangent function of some value u would equal?
U prime
U prime.
over 1 plus u squared.
Okay. Kids, I can't stress enough to you in that far right column how important that column is for shortcuts to derivatives. So you may want to highlight that third column. You might want to draw attention to it somehow. Those are going to be the shortcuts we're using for derivatives today. Okay. Anybody need to see those again to make sure you got those down correctly? Again, it's just a matter of transferring everything that's just a function x into a function u, where u is going to be some more complex function in terms of x. Okay, give me a show of hands if you're ready to move on to the next page here. All good? Far corner, you boys good back here? Okay. Caleb, I admire you today. Still rapping.
A little upsetting.
Upsetting is a nice way of putting it. I knew they were going to lose.
Literally screamed at
Did you? I looked at my dog and said, this team stinks. But not all is lost this year because, I mean, hey.
That is true. Jared Goff was killing it though.
Oh my God. Okay, derivative notation. This is going to be something that's involved with related rates.
That was Jared Goff's first one touch on the day.
It is, isn't it?
Yeah.
I have a quick question for you, friends. You ready?
We beat a Browns fan.
How would you easily solve that?
Top times tops, bottoms times bottoms.
Could do that. Is there a quicker way to maybe simplify? Get rid of the,
7.
this is just going to become what? Okay. Keep that idea in mind because we're going to talk about how we use derivatives in terms of two different rates of change to try and find the type of rate of change we want. For instance, we might run into something like this. We might have the derivative of, say, y with respect to some function r. So we might have y equal to something with respect to r. It might have been y is equal to pi r squared or something like that, okay? And what we also might have in a problem then is the derivative of r with respect to x. The question might want you to find the derivative of y with respect to x.
So you just cancel.
And sometimes we have one derivative, y with respect to r. We've got y prime with respect to r prime with respect to x. What do you think this is going to equal? The derivative of y with respect to x. We are so programmed right now to find one single derivative right here where it says, just find the derivative and they're good. But sometimes we got to understand that what units we're comparing or what units we're trying to find in the end have to match up with what the question is asking. So you might say, well, I've got to find the derivative of y with respect to x, but the only thing I can find right away is the derivative of y with respect to what? Does that match this over here? Not yet, does it? But if I can find now the derivative of r with respect to what?
X.
Multiply them together, what does the derivative of r values do? They go away, and all of a sudden, these two derivatives, or the product of these two derivatives, gives you the derivative of y with respect to what? We're going to see things like that. It's pretty cool. I love that stuff. It's just amazing how it works, okay? All right, let's start talking rules. Oh, I should have probably written those rules down up there. You might have to flip back and forth, okay? Or do you want me to throw them on the board real quickly? I'll do it up here real quickly. Natural log of u equals u prime over u. What do we have? A to the u was u prime natural log of a times a to the u. Arc sine. Ooh, already spelled today. That's going to be u prime over the square root of 1 minus u squared. Our tangent was a new one. Now kids, I want you to understand something. Just because some of these rules are new, do you absolutely dump everything that we've learned already? Do you think some of these new rules might be applicable in a product rule also? Think some of these rules might show up in a power rule somewhere? Maybe a quotient rule? Okay, so we've got to be careful on stuff. First one, natural log, x squared plus x. Oh, I forgot to write one more rule up there. Okay. Anybody want to take a shot at it? What am I going to let u equal here?
U is gonna equal x squared plus 1.
I'm going to let u equal x squared plus 1. So isn't this my rule right here, kids? U prime over u. I'm ready.
2x.
I'm going to say, we'll call these are all f of x functions, or f of t in the next one. F of prime of x would equal 2x over what?
X squared plus 1.
We're done. That one wasn't so bad, was it, friends? Okay. Talk to me about the next one. I see t squared natural log of t. Anything special going on there? Any prior knowledge we have to make this one work?
Well, it's the power rule. It's the
There's a power rule up here, but also this is a product of t squared and what else? Natural log of t. So we've got to understand. So we're probably going to let u equal what here, kids? What are you going to let v equal?
natural log of t.
Okay. Have I relieved any anxiety to this point? I see a lot of head shaking. No, oh my God, I'm failing at my job. How about u prime? 2t. How about v prime? You know this one. 1 over t. My friends, do I have the pieces of the puzzle right there? Can we put the puzzle together now by product rule? So it'll be u prime v. So I always, once I write it like this, I just like to say, okay, it's kind of a crisscross. So 2t times what first?
Natural log of t.
So is it okay to say f prime of t in this case equals 2t natural log of t? Is that all right? Okay, how about uv prime?
T squared times 1 over t.
How about that t squared times 1 over t? Would that simplify it all?
It would just be 1.
Just be 1t right here, wouldn't it? Okay, so here's my first product, 2t natural log of t. So I end with 2t natural log of t plus what?
T.
And there it is. I'm going to be honest with you. I think some of the things that we look at today are actually a little easier than what we saw in the last two sections. Just my opinion. Okay? Oh my Lord. This one's kind of scary.
Skip it.
Roots are probably written to what power, kids?
1/2.
Oh, I didn't want to do that. I wanted to write it to the 1/2 power, Durka, Durka, Durka. Okay, my friends, so this is kind of got a power rule application with stuff on the inside. So if you remember chain rule, where's the 1/2 going to first? We've got 1/2, the whole function, 1 plus natural log of 1 minus y. So what power, friends? To the negative 1/2, and then I need to take that times the derivative of everything that's inside parentheses. So how about the derivative of the 1 part? Any constant's always going to be a derivative of what? 0, right? Okay, so the 1 just kind of goes away. Ooh, we have this thing of the natural log of u, so what would the derivative of that 1 minus y part make? negative 1, right? Negative 1 over u, which is what? You all agree that the derivative inside here then is that negative 1? All over 1 minus y? Would you agree with that? Okay, now to put this probably in a nicer form, I'm probably going to leave the 1 up top with the negative 1. I'm probably going to take this negative 1/2 exponent and move it where? To the bottom, along with the 2 and what else? Here's how I'm going to write this. This is going to be negative 1 up top over, I'm going to call it this. 2, that's this one, times the 1 minus y first. Times, okay, if this moves to the bottom, that negative 1/2 power moves to the bottom, it becomes a positive 1/2 in the bottom, doesn't it? And when you have 1/2 root of anything, it's really which root? So I'm going to probably take this times the square root of what, kids?
Square root of 1 over 1 minus y.
There it is, right there. Now that 2 times 1 minus y, could I distribute there and make that a simpler quantity? Could I have called that 2 minus 2y times that mess of a root? Okay.
Why are we taking that times negative 1 over 1 minus y? I know that it's the derivative of natural log.
Okay, so that's the derivative of all this. So what ends up happening is this. This part right here, the way we wrote it, this part that's in parentheses, the negative 1 power, is kind of like in the top half. And we said, let's move this to the bottom half, which is right here. Okay, so the other parts I was worried about right here then was this 1/2 and this mess right here. Up top, 1 times the negative 1 made your negative 1, which means the 2 times the 1 minus y would have to go in the bottom there.
I don't even remember my question. Oh yeah, where's that? That's on the top coming from. The negative 1 over 1.
Where's the negative 1 over 1y coming from? So this is the derivative of the inside part. Chain rule would say move this out front, keep this all the same, bring that down 1, and then times the derivative of everything inside your parentheses. That was the derivative of everything inside parentheses
Okay.
there.
So what rule are we using with this?
Chain rule.
And
Chain
then what
rule
one of
combined
those?
with
like the chain
your
rule.
new natural log of u rule. Okay?
Listen, I don't like this.
I understand. It's tough stuff. Challenging, isn't it? But one of my favorite sayings. You remember it, Belle?
No.
Gracie, you remember it? If it's not going to challenge you, it's not going to.
Change.
Ah, I love it. So let's try some more challenging ones. Everybody's looking at me like you're crazy parts. You know what? You're right. Gibby would say you are because you drive Chevy. But did you hear that Gibby's looking at a Chevy today? Coming around today. Maybe you should jump on the bandwagon with me.
That's not gonna happen.
No, never. All right, my friends, we're looking at some inverse functions. Now, I'm going to give you an idea here, because some of your problems are nice. Okay, guys, do you agree that the inverse of, I don't know.
I hate how there's exponents.
I have a question. What's x minus x do to each other, really? Okay, what's 1/3 of 3 really do to each other? They're kind of inverses of each other. They just cancel each other, right? What do you think the sign of the sine inverse might do to each other? Okay, so if I had the sine of the sine inverse of x, this would just equal what?
X.
This would just equal x right there. You might want to jot that down. That's an important one, okay? All right, so the first thing we're looking at in this example too is I want the derivative of the tangent inverse of t squared, okay? Well, I look at my rules over here, not so bad. It's u prime over 1 plus u squared. What do you think you want u to equal, kids? Okay, so my derivative right here, in this case, with respect to t, f prime of t would equal, what is u prime up top? 2t.
Could you do t to the 4th?
You could do t to the 4th, and watch the way I'm going to write this. I'm going to write this as 1 plus t to the 2nd, all to what power? Right? Question came up, could I call it t to the 2nd, t to the 4th? The answer to that is 100% yes. So f prime of t, probably in simplest form, I'd probably call it 2t over 1 plus t to the 4th. Very good. Ay, 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 ay. Next one's an interesting one. Okay, first of all, everything with respect to theta, right? What do you think you're going to let u equal here? You want the inverse sine derivative, or the derivative of the inverse sine of the tangent of theta. I'm going to let u equal the tangent of theta. Okay, anybody recall the derivative for tangent? Oh, this is where the cheat sheet comes in. So you might have to go back to 4.5. I'm pretty sure it's 1 over cosine squared.
Which, u prime over cosine squared u.
So it would just be 1 over cosine squared, because we would let u equal theta then, right? And theta is just like an x, so the derivative of 1 theta would just be what? Okay, so in this case, u prime is going to equal 1 over cosine squared of theta. All right, here we go. Here we go. By rule, the derivative of the inverse sine function is u prime over what?
1 minus u squared.
Okay, so what is u prime again, friends?
1 over the cosine squared of
So
theta.
here we go. F of theta, or I'm sorry, f prime of theta is going to equal that u prime, which is 1 over cosine squared, all over, anybody want to take a guess?
1 plus tangent of theta squared.
It's 1, we're doing the inverse sine, kiddo.
Oh, so the square root of 1 minus tangent of theta squared.
I'm going to call it 1 minus tangent squared of theta. Messy, isn't it? Okay, I'll keep the recording going, you guys that are taking off, and if you want to catch the last whatever, that'd be cool, okay? All right, let's talk about this next one, my friends. Guys, anytime I have e to the natural log of something, what's this e and natural log kind of do to each other right here?
Cancel.
So this is going to cancel this, so f of x in this case, sometimes it works to your advantage to rewrite this. This is really going to be e to the 2x squared plus 3. Now, if you recall, derivative of e to the u is u prime e to the u. So in this case, if I let u equal this far up here in parentheses, what's the derivative of that? See you guys. Have a good day. What's the derivative of 2x squared plus 3? 4x, right? So f prime of x will be that u prime out in front. 4x times your e to that power again, 2x squared plus 3. Okay? So in that example right there, was it to our advantage to maybe rewrite or simplify first before I went with it? Yeah. Okay, so you might make a note right up here. Go from this step to this step right here. We didn't take a derivative right away. We said, let's simplify this first. Simplify that first, and then take your derivative, if that's an option. Okay? Guys, would I expect you to remember exactly every single rule all the time?
No.
It'd be great if we did, but we're at least be resourceful and have these, okay? Be resourceful and have these. Understand the concept of the chain rule and how that works for each specific case. I think you'll be in good shape if you do all that, okay? Double check, make sure you have everything down. And let's move on to page 3 here. Did I need to go back on that? Were you guys good or not?
Good.
Good? Oh my gosh, example 3. Let's talk right here. This is an interesting type of problem right here, and it's interesting about inverses of functions. Guys, if I gave you a point like 6 comma 4, what would the inverse of that point be? If I gave you a point on a graph, 4 comma 6, where would the inverse get graphed? What do you do with inverses in terms of x and y?
4, 6.
Switch them around. So 6 comma 4 was a point. Where would the inverse lie? 4, 6. Okay. Guys, the core concept we're going to talk about today is this. It says the derivative of the inverse is the what? Reciprocal of the derivative of the what? Okay. Okay, listen to what I say here. The derivative of an inverse is the reciprocal of the derivative of the original function evaluated at the point f inverse of x instead of what?
Instead of the point x.
Okay. What's the derivative of this? So what would f inverse of x equal? If I wanted f inverse prime of x, I guess. If f prime of x is 6, what's the reciprocal of 6? Okay, 1, 6. Okay. Guys, I have a table of values for a graph down here. Let's talk about it. Okay. It says figure 3.29 shows f of x and f inverse of x. And it says use table 3.6 to find the following. Okay. So the first thing that we have is all these x values, 0, 1, 2, and 3. F of x is equal to a value of 1, value of 2, value of 3, and a value of 4. Okay? Now, this gets to be pretty interesting here today. First thing that they're going to ask you guys is use the table to find the following. Okay? First thing they want is just f of 2. Okay, I plug 2 in for x. What's f of 2 equal, guys? Okay, well, f of 2 in part A would have to equal 4. When your x value is 2, what's f of 2? 4, right? Okay. Now the next one is a little different. The next one is saying what's f inverse of 2? In other words, they're saying what was the x value that was put in to get an output of 2? So in this case, f inverse of 2 would fall here, kids. To go from inverses, you'd have to work kind of backwards right here. So if I do an f inverse of 2 right here, kids, what would f inverse working backwards be for that x value? So it's kind of like saying f of x, in this case, I should back up here. Let me back up here. For this particular row, this is saying f of 1 is equal to what value, kids? When I plug 1 in for x, what's my value f? 2. Now by inverses, what do I do with x and y? So this would mean f inverse of 2 would have to equal 1. Now is that 2 for an inverse coming from this column or from this middle column? Okay. So in this right here, f inverse of 2 would have to come back to or map back to what value? 1. Okay. Are you with me on the first two parts there? Okay. Third one says, what's f prime of 2? Guys, well, what is f prime of 2? At x equals 2, what is that?
2.8.
Okay, so you know that f prime, that's easy to figure out from a table, isn't it? All right, this last one is where I get really worried. This time they want the derivative, they want f prime, what's the fourth one say? F prime inverse of what value? 2. Okay. Guys, the derivative of the inverse of 2. Okay, you just got done telling me the inverse of 2 was what, kids? The inverse of 2 is really what? 1. So wouldn't the derivative of the inverse of 2 be the same as, okay, listen to what I say, or be the same as the derivative of, where did f inverse of 2 map back to?
1.
Wouldn't that be the same as f prime of 1, but then take the, what did they say in there? The derivative of the inverse is the reciprocal of the original function. Okay, you guys agree that f inverse of 2 is the same as f of 1, right? What's the slope at f of 1? But since we're doing the derivative of a inverse, it's got to be the reciprocal of what? So this is going to equal 1 over what? Aye. Let's see how good you are. Oh boy. I'll try this right here. I don't know, you guys. I don't know. Should we try this one? F inverse prime 4. Okay, first question. What would the inverse of 4 map back to? 2. So the question becomes, what is f prime of 2? What is f prime of 2? 1 over 2.8, yep. F prime of 2 would be what here, guys? 2.8, but we want, since we're doing the derivative of an inverse, you want the reciprocal to be 1 over 2.8. Holy cow. Okay, we'll visit some stuff together on that when we get going through assignments on that, but you're going to see there. That is some tough stuff. Now, is there a part B to this question, kids?
Yeah.
What's part B asking us?
The equation of the tangent lines at the points P and Q.
Okay, let's do point P first. Okay, the equation of the tangent line at point P. Okay, do you guys agree that the point P is at the point? Gosh, it looks like I could go over right 2, is it 3, and then up how much? 8. You guys agree that this point is 3 comma 8 right here if we look at this graph?
Yeah.
Okay, let's write this down for point P. Point P is at 3 comma 8. Okay, so that means, kids, we probably need to know the derivative at what x value? Okay, this table is telling you the derivative at x equal 3 is what? 5.5. So if I drew a line of tangency right here, this table's already given us the information we need. If I drew a line of tangency right here at 3 comma 8, they are telling you that the slope of that line right there is how much? 5.5, right? Okay, from this table right here, I can see that at x equal 3, ooh, I can't see it anymore. At x equal 3, slope is 5.5. So the equation for my line of tangent, I'm going to write down my tangent here. I'm going to start slope intercept form. It would be y equals, what's the slope again here, kids? 5.5 times x plus b. But guys, that line with slope of 5.5 is passing through which point? Which states when x is 3, your y value must be what? 8. Okay? Roll with me on this. What are you plugging in for y? 8 equals 5.5x, which the x value said was 3 plus b. Kids, this becomes 8 is equal to 16.5 plus b. What do you guys get for your b value there? Negative 8.5, very good. Okay, negative 8.5. Okay. So once b is negative 8.5 and your slope's 5.5, can we come up with a tangent line equation now? So we get y equals 5.5x minus what? Okay, now here's the interesting part about this. Okay? They also want an equation for which other point? Q. We've kind of done the work for this already. What we talked about, these two things in red over here in part A, were they kind of difficult to figure out? Okay, here's what's really happening. Those two parts in A, visually, here's what's happening. Guys, we also want a tangent line equation at what other point? Q, which is really which coordinate? How is 8 comma 3 related to 3 comma 8?
They're inverse.
They are inverses of each other, right? And if these 2 points are inverses and the 2 graphs that are graphed are the original f of x and f inverse of x, this states then at the inverse point, the slope at this point for an inverse function is the reciprocal of that slope. And that slope was what value? Which means if I drew a line of tangency in here at Q, it would be the reciprocal of 5.5. So what's the slope of that line going to be?
1 over 5.
I have a quick question for you, friends. Do we know the slope? And do we know the point which we'd like to travel through? I say we figure out this equation and call it good today. How's that sound? We'll pick the rest up tomorrow. Okay, so let's roll with this. What point am I concerning myself with that Q? 8 comma 3, which is the inverse point of P given original function and inverse function. All right, no problem. Let's roll. Okay, and I should write down this first one was a tangent for which point, kids? Okay, so let's do the tangent for Q right down here. Okay, so I'm going to say y equals 1 over 5.5. Do we understand that slope 1 over 5.5 now? Does that make a little better sense than what we were looking at in the table? 1 over 5.5x plus b, given which point to plug in for x and y? 8,3 says when x is 8, y is 3. So here we go. 1 over 5.5 times 8 plus b. Oh, my lord, kids. 16 over 11, I have no idea what this is going to be. Is this 0.15? I don't know, I can't be. 16 over 11. 1.45 repeating, so I'm just going to call it 1.45. Is that okay? So I've got 3 equals 1.45 here. Okay. So subtract 1.45, I've got 1.55. Is that true? Okay, so what's our final equation on Q, kids? 1 over 5.5 times x plus 1.55, right?
Yeah.
Very good. Okay, let's go ahead and stop there. We'll pick up, we don't have much left for tomorrow, so you'll have a little bit of time to work on some things tomorrow, I think.